Alright, this is a formula that we just derived. So the covariance matrix working on A1 gives a result lambda A1. That means that A1 is an eigenvector of the covariance matrix. Remember, the sigma is the same as covariance X, is also the same as variance X, when X is a vector. So we substitute now in the variance of Z1, we substitute the covariance X times A1 by lambda A1, and the outcome is lambda because A1 transpose times A1 again is the size of the vector A squared, but it's a unit vector, so 1 squared equals 1, so you get lambda. So the variance along the A1 direction is the eigenvalue lambda itself. Okay? Now the eigenvector A1 corresponding to the highest eigenvalue of that covariance matrix is the first principal component. So we found our first principal component. Now we're going to try to find the second principal component. And there is a second constraint. Remember here? So the second constraint is that A1 transpose A2 equals 0. Is the same thing as A1 dot product A2 transpose. It's the same. So now if we rewrite the Lagrangian as we did a while ago, but now we apply it to A2, so that is A2 transpose covariance X A2. That's exactly this, but applied to A2. Minus alpha, and I have that A2 transpose times A2 minus 1 equals 0. That was the first constraint, but now I replaced A1 by A2, and now we have a second constraint. It's minus beta A2 times A1 transpose. This is the second constraint. Now we're going to have to take the gradient of the Lagrangian and set it to 0. So the gradient of the Lagrangian, and so we derive with respect to A2. This means A2 squared, so I derive is 2A2 covariance X minus, if I derive with respect to A2, meaning 2 alpha A2, right? And here minus beta A1 or A1 transpose. It doesn't really matter. So we set that to 0. Okay. So now what we're gonna do is we're gonna multiply this Lagrangian with A1 transpose. So let me actually put it a bit lower so that we have space. So Lagrangian times A1 transpose equals 2A2 covariance X A1 transpose minus 2 alpha A2 A1 transpose minus beta A1 transpose times A1. So what I did is I can take this transpose away here. it doesn't really matter, yeah, because here I can swap as well. It doesn't matter, it's beta A1 or A1 transpose, and now I multiply with A1 transpose. Okay, so if we set this to 0, yeah, what we're gonna do now is here we're gonna swap A1 and A2. Can I do that? Yes, and the best proof is to use an example. You have two unit vectors. One vector is 1, 0, the other one is 0, 1. And you take a symmetric matrix and you do the calculation, you will see it's the same. I'm not going to do it here. So this becomes 2 A1 covariance X A2 transpose. Okay. Here what you see is that this term is 0 because A1 and A2 are perpendicular, so the dot product is 0, and A1 times A1 transpose, this is 1. Yeah. So what else I'm gonna do? So I see here I also have A1 covariance X is this one here. So I can replace by lambda A1. This I can replace by lambda A1. Yeah. So that means that Lagrangian times A1 transpose equals 2 lambda A1 2 lambda A1 times A2 transpose minus beta must be 0. Yeah. Now here you see this is already 0. Yeah. So that means that beta must be 0. Okay, so now that we know that the beta is 0, we're gonna put it in this equation. Yeah. So this equation becomes 2A2 covariance X minus 2 alpha A2 equals to 0. Yeah, so we can take the 2's away here, and here we have that covariance of X A2 equals alpha A2. So okay, this is the same as this formula. So A2 is also an eigenvector of the covariance matrix. Yeah? So A2 is eigenvector, eigenvector of the covariance matrix, and the eigenvector corresponding to second highest eigenvalue is second principal component. Okay, conclusion, the covariance matrix has the eigenvectors, where D equals the dimension of the feature vector X. Yeah. The covariance matrix is symmetric. Remember, we have the variances on the diagonal, and you have the covariance outside of the diagonal, and the eigenvectors A1 all the way to AN are orthogonal. So A1, 2, I would say not AN because we say D dimensions, so it is AD, are orthogonal. Yeah. Since we talk about variances here on the diagonal, yeah, variances are always positive. Yeah, so the eigenvalues will be positive. Huh?